Hi, it's Science O'Clock. Welcome, guys. We are going to be learning about fullerenes and graphene. I believe Mr. Hab has been setting you lessons until now. You have me for a period of time. We're going to look at, you're going to be able to describe the structure and properties of fullerenes and graphene by the end of today's lesson. There's also a worksheet for you to do. The starter, though, is can you just name the different types of bondings that there are in molecules? You should have been doing that from the previous topic. Can you give an example for each one? So, pause, write it down, and I'll give you an answer example in a minute. Oh, wait. Have you done that? Excellent. Well, let's see. Here are my examples as I move on to the next slide. Oh, the mouse is gone. Okay, so first one, ionic bonds. Ionic bonds, hopefully you wrote that down. An ionic bond is between a metal and a non-metal, and an example would be sodium chloride. Sodium is a metal, group 1, and chlorine is a non-metal in group 7, sodium chloride. Covalent bonds. These are between non-metals. Examples are something like water, which is H2O, or you could just have a simple covalent bond in a hydrogen molecule, H2. Another example could be a giant covalent structure, and diamond is an example of a giant covalent structure. We are, though, not looking at anything giant. We're going to look at things that are very small. So just to renew or give you something information, my head's in the wrong place, but it says nanotechnology. What is nanotechnology? It's things that are very, 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 very small. Nanotechnology is looking at things that are nanoscopic, which is smaller than microscopic. Things that are very small things are called nanoparticles. Comes from the Greek word which means dwarf, and a nanometer is a 0.000000001 of a meter. If you know standard form, that's 10 to the minus 9 meter, or a millionth of a millimeter, a billionth of a meter. Take 1 meter, divide it into a billion equal segments, and each one will be classed as a nanometer. Nanoparticles are very small. Okay, first task. So in a minute, you're going to have to write things down in your book. So the first thing I want you to do, we've got millimeters, centimeters, micrometers, kilometers, nanometers. Can you put those in order? Let's go from the biggest to the smallest. So put those in order. Then, can you write down what we use to describe them? So for example, I'll give you one of them. Centimeters, we write the letter C. Centimeters, C-M. Right, what do you use to describe all these ones? And do you know any more? So milli, centi, micro, kilo, nano. Do you know any more of them? If you do, write them down. I'll pause and I'll give you some answers in a second. Have we done this? Even you? Yes, excellent. Well done. Right, let's check your answers. Okay, going from the biggest down to the smallest, the ones that you need to know. Biggest that you need to know is giga. Giga, we do it in standard form, is 10 to the 9, 10 plus 9. Gigameter is a billion. So a billion meters is a gigameter. Mega is like a million, 10 to the 6. And kilo is 1,000, 10 to the 3 standard form. Centi is a weird one because it doesn't fit the other ones. Look, they go, where's the mouse pointer gone? They go 9, 6, 3. So they're going in 3. Centi doesn't fit the pattern because it drops down 1. But it's a common one, so I thought I'd put it in. Centi is to the 2. Then we go down to the negative. So these are smaller than a meter. Millimeter, 10 to the minus 3. Micro, this is the Greek letter mu. Mu. And it looks like that. So it's like a U with a line in front of it. It means micro, that's 10 to the minus 6. And nano is one below that, 1,000 times smaller than a micrometer. And that's 10 to the minus 9. Did you get that right? You did. Well done. Have a tick. How small? Okay, so I'm going to use this strange animation, which is like a fuzzy hair person with a pot belly. Belly sticks out. It's a child, apparently. If you look like that, I'm sorry. I didn't mean you look strange. Okay, this child is about 1 meter high. That's the same as 1 billion nanometers. Let's go down. What's smaller than that? Apparently nothing. No. Right, there we go. Down. Let's zoom in. Okay, yes. So your hand, it says, is about 10 centimeters across. Do I have a ruler here? Let me use my hand. I don't have a ruler. I got one, sorry. I think mine's probably slightly bigger than 10 centimeters, but your hand is about 10 centimeters. That's 100 million nanometers. 100 million. Your hand. If you tell someone your hand is 100 million, now they think you'd have a massive hand. You don't. Your fingernail, 1 centimeter. 10 million nanometers. Next one. The head of a pin, 1 millimeter. Only 1 million nanometers. Pretty small. The human hair is 80. What's that symbol? Micro. 80 micrometers. Very small. That's the same as 80,000 nanometers. What's the next one? This delicious looking red donut. That's actually a red blood cell. 10 micrometers. 10,000 nanometers. Where do we go next? Where's the mouse gone? Who knows? There it is. A bacteria. Oh, look at that hair. It looks like a bogey that's been rolled in hair. That is 1 micrometer. 1,000 nanometers. Oh, the HIV virus is approximately 100 nanometers across, which is about the same size as the coronavirus, keeping things topical when you're locked down at home. Cold, smaller, only 20 nanometers. Looks like a spiky lemon. Hemoglobin molecule, so that's what makes your blood the color it is. 7 nanometers across. And then if we're going down, a carbon atom is about 0.1 nanometers. So there we go. So when we're talking about nanometers, we're talking pretty close to the size of an atom. Very, very small. So these aren't things you can see. In fact, so if we go up here, where is it? Up here. Boink, 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 boink. This is smaller than light. So you can't see a HIV virus with light because it's smaller than light. So you need something special to be able to see these. And in fact, in 1981, they invented something called the scanning tunneling microscope, which is an amazing machine that allows you to see using an electron. The electron is the smallest thing that we know of today, and they use an electron that jumps this kind of, it tunnels, which is kind of quantum teleportation, and it jumps from the needle onto the slide, and it allows you to create an image. It's basically the microscope that allows you to see the smallest of things. They managed, here we go, in 1989, the scanning tunneling microscope was used to remove 35 xenon atoms on a tiny piece of nickel. The atom spelled the name of the company that the scientists worked for. What was it called? IBM. There we go. If you're not sure, it says IBM Research at the bottom. Nanoparticles, some of the things that makes them quite cool is that they have a really small surface area to volume ratio, which you should remember from before. If you chop things really small, you get reactions happening faster. So this, for example, if this was like a whole potato and you just put it in a saucepan to boil, it might take half an hour to cook. But if you chopped it up into lots of tiny little pieces and you put it in the same saucepan, that small pieces would cook really quickly because they have much higher surface area than the whole thing. So that's useful. Okay, but now we're on to the meat of it. There's a lot of information, so sit back, relax, but maybe take some notes. You know about diamond. It's a giant covalent structure. But what is it made of? It's made of carbon. Carbon is one of the allotropes of diamond. You can also have graphite. The difference between diamond and graphite is diamond, all of the carbon atoms are, I'm trying to model with my hand and I can't, all the carbon atoms are joined together, so every atom is joined to another atom. Whereas graphite, they're all joined together in a layer, but the layers are not joined together. So like sheets of paper, all the atoms in a sheet of paper are joined together, but they're not joined to the page below. And so they're missing one of those kind of extra bonds. So graphite, diamond. So they're quite common, but actually there are other ones called fullerenes, which is what today is all about, and we're going to introduce you to some different fullerenes. And they're closer to graphite than they are to diamond, I suppose. The first one of these was called the Buckminsterfullerene, discovered in 1985. And that's what it looks like. And it's basically, hang on, go back one. It's basically a ball of carbon atoms all joined together in this kind of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, yeah, 5 pointed hexagon type shapes. And so they're all joined together and they make these incredibly small, but incredible tiny particles that have amazing properties. The properties of the Buckminsterfullerene is they're black at room temperature and they're solid. They will not dissolve in water, but they do dissolve in petrol. Handy. But the most important thing about these is they are incredibly strong. They are so strong. They are much more. They are relative to their size. They are stronger than all other known materials, and they're so strong you can squash them so much, like 70% of their normal size, and they will just boing back to the original size. They have a crazy properties. They have other chemical properties. We can use them as a kind of cage for certain atoms to trap other atoms and molecules in. If you coat them with another atom, the surface can be coated with other atoms, making an incredibly smooth surface. You can make things very smooth, and you can make bigger ones, kind of like Lego. There are other ones. There's the C71, like a rugby ball. There's a Bucky Babies with the less than 60 atoms. There's a fuzzy one with hydrogen, and there's giant fullerenes, which are big. So fullerenes are just these kind of complete structures made of carbon atoms, sometimes with other things, but they form a ball or they form a kind of ball. Sometimes they're perfectly circular, sometimes they're more rugby shaped, but they form a ball. That's what a fullerene is, a complete like ball cage of these carbon atoms. What can they be used for? They can be used to make things incredibly smooth, so they don't have friction. They can use them for medicine because they can be used to hold drugs that can be delivered straight into the body, and we can use them also as a kind of sieve to extract viruses from things, so like a virus sieve, which is pretty cool, be handy at the moment. And they can use to soak up toxic substances in the body. Why did you put toxic substances in your body? Who knows? Okay, other types. There are other types. Nanotubes. I know loads about nanotubes. I'm a nanotube expert. Ask me anything. Go on. No questions? Okay. Nanotubes are they are graphite, a sheet of graphite that have been rolled up into a cylinder, into a tube, a nano tube, nanoscopic type of tube, and they're rolled up into a cylinder. This is what I studied at university because I'm that cool. They are even stronger than kind of the Bucky balls and the fullerenes there. So they've got incredibly high tensile strength. Compared to the other normal materials, they are the strongest thing out there. They have very unique electrical properties. If you roll them up that small, you can almost get one electron through it. They can incredibly great electrical properties, and they're very good at heat conductance, as in they allow heat to travel very easily. Going to jump through this. But graphene is if you take one of them and unroll it. So you take a carbon nanotube and you unravel it, you have a sheet of graphene. Another way to do it is to get graphite and maybe like put a piece of sellotape over the top, and then if you peel that sellotape off, and what you have stuck on the sellotape is just like a single sheet of graphite. Again, like the fullerenes, like the nanotubes, these are incredibly strong. They are so strong, they put all other materials to shame. They are amazing electrical conductors, and they're very low density. The idea with these things is you can miniaturize things like computers so much because you can make them so small because these have got great electrical conductivity. They're really strong. They don't really get damaged by heat that much. So they have awesome properties, which is definitely something that people are using. Problem is they're really small, so not very easy to build things with. But currently, because of carbon nanotubes and graphite, we have thin TV screens. We've got small optical fibers, waterproof things. Because of their properties, they're very good at waterproof. But most importantly, they make things incredibly strong. Their cars have carbon nanotubes and carbon fibers put in them to make them stronger. Other building materials, if you have graphite, if it was made just of graphite, it would be incredibly strong. And they can, because of their electrical properties, they can make electrical circuits so much smaller than they already are. You can miniaturize things even further, and the technological ideas are really quite exciting. Okay, so there's loads of information. I'm sorry, but what you can do to take it further is there is a worksheet for you to do as well to go along with this. Okay, thanks. Love you. Bye.